All right, so let's talk about a couple of terms that we have for harmonic functions that we had for holomorphic functions, and actually there are functions that hold for a wider class of function. The identity holds for harmonic functions because they are real analytic, and the maximum principle is well, in some sense it's a theorem about harmonic functions, but in some sense it's a theorem about solutions to elliptic partial differential equations. So it's probably the simplest correct context for maximum principle. It's the maximum modulus principle is really is really in some sense a special case of the maximum principle for harmonic functions, which is the more correct setting maybe to look at it. Although we will prove both of these terms using what we've proved about holomorphic functions. So it is not, in some puritanical way, it's not the most correct way to prove them, but we've already spent time proving stuff for holomorphic functions, and they follow quickly like this. Otherwise, we'd have to figure out more about for identity. We have to figure out how power series in two variables work, and for the maximum principle for harmonic functions. Well, we'll actually see how to prove it more correctly, the mean value property. But for now, the holomorphic functions just give us an immediate, quick proof, which will be useful. So, all right. So let's start with the identity theorem. So the identity theorem for harmonic functions is slightly different. So for holomorphic functions, it's that the zero set is if it has limit points, then f is identically zero. Now, it's not that's not the case for harmonic functions. For example, real part of z is a harmonic function, and yet it's zero on the entire imaginary axis, and that clearly has limit points and is not an identically zero function. So it's a little bit different, but we still have this idea about if there is an open set inside the zero set, then the function is constant, identically zero. Right? So this is what the identity term for harmonic functions is. If we have a domain, if we have function f on U, it's harmonic, and we suppose that there is a V, which is a non-empty open subset, and on V we get that f is zero. Well, then f is identically zero. So how do you prove it? Well, let's let z sub f be the zero set of f, and let z be the closure of the interior of z sub f, and the closure is in the subspace topology, right? Now, maybe this is a couple of words, but it's basically we don't z sub f a priori could have it could be it's going to be a closed set z sub f, but it maybe has some weird components somewhere a priori. It's not going to, but a priori it could, and maybe it has some interior. We're going to assume that this interior is open. Oh, it's non-empty. Sorry, interior is open, but it's non-empty. And so let z be the closure of this interior. So we don't care about these points where f is an isolated zero or something. We just care about the points where it's really zero on an open set, and we want to take the closure of it so that we have a closed set. Now, Z is still a subset of Z sub f because that is a closed set to begin with, right? In the subspace topology, right? In U. So suppose this the interior is not empty, therefore the set Z is not empty, and let P be some point in Z. If you take a disk around P such that this entire disk is in U, well then F is zero in some open subset of this disk, right? Open subset of this. Why? Well, it's Z was the closure of the interior, so either P is in the interior of Z sub f, or it's on the boundary of the interior of Z sub f. In either case, if you take a little disk around P, you're gonna hit some points from the interior of Z sub f, right? So that means that f is going to be 0 on some open subset of this disk. Now, there exists a harmonic conjugate in this disk, right? Because this disk, well, yeah, just like any disk, is simply connected, right? So we know that we can find on this disk f is the real part of a holomorphic function, so therefore there exists a harmonic conjugate, right? So f plus ig is holomorphic, and it is purely imaginary on an open subset of the disk, wherever f is 0, right? On the 0 set of f, well, we just have ig, so yeah, it's f plus ig is purely imaginary there. That means that f plus ig is constant on some well, at least on a subset of the subset, right? I mean, on some small piece of it, this holomorphic function must be constant, because if I have if I take a holomorphic function and it's purely imaginary on an open set, and suppose that that open set is connected, then it is constant, right? Well, but that means that this holomorphic function is constant everywhere, right? That's the identity theorem for holomorphic function, right? So that means that it is purely imaginary on this entire disk, right? Which means that that f is 0 on this disk, right? Well, that means that Z is actually an open set, right? So we started, it was clearly closed in U, and now we're saying, well, it's actually open as well. Well, so Z is open and closed subset of U. It's not empty, and U is connected. It is a domain, right? Then that means that Z is equal to U, and therefore f is identically 0. All right, so that's the identity theorem for harmonic functions. All right, so let's look at the maximum principle. So it starts very similarly. Suppose that U is a domain, and that f is a harmonic function on U. And let's suppose that f attains a local maximum or a local minimum, right? In here it doesn't really matter. Then f is constant, right? That's the conclusion, right? So a non-constant function cannot attain a local minimum or a maximum inside the domain, right? Just like for the maximum modulus principle. Now you have both maximum and a minimum principle, really. But really, it's, once you have it for a maximum, you have it for a minimum, because if f is harmonic minus f is harmonic. So he also, it's really this theorem will follow from the mean value property, which is sort of well, the similar property that we've seen for holomorphic functions, and that's really the way that we proved it for holomorphic functions. But so that we don't have to, that we get a quick result right now, and we don't have the mean value property yet, we will have it soon. Well, let's just use the maximum modulus principle for holomorphic functions. Actually, what we're gonna use is it's simplest to just use the open mapping theorem. Actually, seems to me that the simplest proof. But maybe, philosophically, the right way of doing it is through some sort of mean value property, maybe, for harmonic functions. That's really sort of the feels more correct about why this is true. Holomorphic function is going to be basically it's an average of its values nearby, so it can't really have a maximum or a minimum somewhere. Well, it's, similarly as it was for holomorphic functions, although there was a slight difference there. All right, now it's also this maximum principle implies the regular maximum principle for holomorphic functions in a fairly simple way, by just considering the logarithm of modulus of a holomorphic function, which we know is harmonic, right? And applying the maximum principle to that harmonic function gives you the maximum principle for maximum modulus principle for holomorphic functions, and it actually gives you the minimum principle that we've seen in an exercise, right? That a holomorphic function, the modulus of a holomorphic function cannot attain a minimum unless it's 0, right? Okay, so these two, the maximum principle for harmonic function is equivalent to the maximum modulus principle for holomorphic functions. There, we can prove one from the other. Okay, so without loss of generality, as I said, let's suppose that f has a local maximum at some point p. Otherwise, just consider minus f. I noticed I misspelled maximum. Maximum. So if it is a global maximum on some disk, right? If it's a local maximum, then on some small disk, it's definitely a global maximum. So it's a global maximum on this disk. Well, this disk, maybe U isn't, but this disk is simply connected, right? So therefore, there exists a holomorphic function, let's call it H, such that f is the real part of H, right? There's a holomorphic function on this disk, right? It's not defined on U, but maybe, maybe on a larger set than this disk, but definitely on this disk, but not necessarily on all of U, but we don't need it on all of U. So if we look at where H takes the disk, what's the image of this disk, which is an open set, right? So H takes this disk, so the image of the disk is, it's the set defined by this this equation. Well, that's precisely what it means. The real part of W, well, we're really taking the real part of H, right? And we know that the real part of H achieves a maximum at P, right? So therefore, the real part of H cannot be bigger than f of P, right? be equal somewhere, but cannot be bigger than that. Actually, at p, h of p, the real part of h of p is equal to f of p, right? So that's when we have an equality over here. So that means that h of p is on the boundary of x, right? It's because the boundary is given by an equality over here. All right, it's basically this half plane, right? Well, but that means that the image of the disk is not open, right? Because the h of p is not in the interior of the image, right? This is x, right? This is the image. But that means that h is constant, right? Okay, h is only defined on this disk, but now we know that h is constant. Therefore, f is constant on this disk, right? But U is a domain, it's connected, and we just proved the identity theorem. So if f is constant on an open set, it is constant on all of U, right? And so we have the maximum principle. Okay.